Welcome to Finite Element Methods. Today I have an invited guest speaker, Dan Mueller, and he's going to talk to us about some lessons learned and some awesome ideas. So I'm going to pass it over to Dan Mueller. Thank you so much for coming to class and talking to us about the experiences that we should keep in mind when dealing with finite elements. Thank you, Dan. Over to you.
Yeah, cool. Thanks for the intro. As mentioned, I'm Dan Mueller. Vinay and I worked together for about 5 years before I moved to Germany. So just a little bit about myself. So I graduated from, University of Wisconsin and USC. This was back in 2015. I got my master's in aerospace engineering. Vinay was one of my professors. So it was cool. And then in terms of where I've worked and what I've worked on, I actually started my career at the Boeing company as a structures analyst. Worked on a couple of programs there. One was called ELASA, which was basically a tiny rocket underneath an F-15. I was the structures engineer for this composite pressure vessel structure. And then Echo Voyager, which is shown up there on the top right, which is unmanned submarine structure. I worked on the structure, but it was an unmanned submarine. So I did a lot of the sizing for that. Lots of FEA involved in both of those topics. It's kind of where I developed my some of my chops in being able to use tools and do sizing and actually release parts that get flown, or rather not flown, but swim. And then after a couple of years at Boeing, moved on to SpaceX. I was there for about 4.5 years in total. Started as a structure certification engineer, which is I think a bit of a confusing name, but it does a lot of stuff. It's kind of hard to explain. I worked on nearly every thing at the company that had to do with structures. So Falcon 9, Falcon Heavy, Crew Dragon, and a few other development programs, basically trying to get everything certifiable. So in terms of structures, this is really focused on structures, but also a bit of system level work as well. So for example, getting Falcon 9 certifiable for national security missions. This was something that Vinay and I worked on a lot. We did a lot of really interesting work together. Likewise for NASA Crew, good example there would be, it's quite relevant to this class, is reviewing all the finite element models that were being given to them, resolving issues, in some cases doing some of this work myself, and then a lot of fracture and reuse work for being able to land and reuse rockets. I also was very involved in 2 of the failure investigations that happened. We had Flight 21, where we lost the vehicle. That's shown there on the right, kind of second looking picture there. And then we call Flight 29 was one where we had a rocket blow up on the pad, which was a composite override pressure vessel failure. Again, another very relevant FEA topic where we were spending lots of time trying to develop models that were accurate about how a composite override pressure vessel might fail. So I did that for, I don't know, about 3 years-ish, and then moved into more of a lead vehicle role. So took over the function at SpaceX of developing structural analysis methods and tools. So this was basically rolling out processes, design criteria that people could use, and anything related to structural analysis. So FEA was a huge part of this. We also did a lot of other things. We made a lot of really kind of, I call just like easy desktop tools like spreadsheets to size things, released a lot of design guide type material. That was pretty fun. And then I was the lead design criteria engineer for the Falcon 9 Block 5 upgrade, which is the one you see flying today. So it's the one that is 10x reusable, I'm sure it'll fly more than that at this point. And then also being able to fly Falcon Heavy and crew certifiable plus national security certifiable. So really rolled in all the kind of work that we did with our certification authorities. So at the time, this was EELV. I think it has a different name now, but them and then NASA crew. So kind of getting all that put together.
Hey, Dan, I have a question for you. One
Yeah,
of the questions that keeps coming up typically is that early in your career, you may not know where you're going. So in 2012, do you know you're going to work on rockets? Like, what was your mentality back then?
yeah. I mean, yeah. By the way, anybody can just stop and ask me questions. That's probably the best way to do this. But I had just a goal to always be working on well, two things. To always be working on interesting projects. So whatever I thought was fun to work on, because that's your like that's your day to day, is you have to feel like you like working on what you're doing. And for me, that was working on fun projects. So submarines or rockets or whatever. Definitely rockets are pretty high up on that list. I didn't go for rockets right away, but it turned out that I really liked doing it. And the second thing is working with good people. So actually, that was kind of the reason I moved from Boeing to SpaceX, and kind of I always feel like it's good to work with people that you're constantly learning from, or that are I don't know. Usually, I think about, do you feel like they're smarter than you? Can you learn something from them? And if the answer is always yes, you're probably in the right place. So I kind of just gravitated towards SpaceX, to be honest.
That's a really interesting idea. So basically, surround yourself with people that know more than you so you can learn from them, right? That's kind of what you were doing.
Yeah, and if you're always feeling like you're the smartest one in the room, generally the time to keep looking, because there's definitely people out there who are smarter than you. It's a given for sure. Yeah.
That's a very cool point of view there.
Yeah. Cool. What does it mean to lead design criteria? Okay. Design criteria is also a confusing word, but it's important. So SpaceX used the term design criteria as a bit of a catch-all for systems engineering. It wasn't really that. But design criteria was, just to give a concrete example, basically, how do you design your hardware? What are you trying to do? If I want to put something on the rocket, how am I supposed to do that? More or less, it's fairly simple. Well, it's actually very complicated, but in a short description, that's what it is. Good. Okay. Then from SpaceX, I took a bit of a not a U-turn, but a hard left, and decided to take a job in Germany. So I took a job with a company called Lilium. This is where I'm currently working. So at Lilium, well, rather, what does Lilium do? I should explain that first. So in the bottom right-hand corner, you can see the vehicle I'm currently working on. But Lilium is an electric aircraft company trying to develop basically air taxis. So promoting urban mobility, and also connecting some regions of the world that are not that well supported. And also, it's a bit of trying to move into a sustainability mindset. So developing new novel aircraft that are fully electric. So starting in November of 2019, I was onboarded there as a senior mechanical engineer, doing basically layout and structural sizing. This is for the fuselage, which is actually for the whole structure of the vehicle for our 7-seater eVTOL air taxi. And I provided a link there to some information there on what that looks like for at least what I can share. That's our investor pitch, so everybody can have that. That was super fun. I did that for about 7 months. Basically, was me working with the chief engineering function at the company, who were trying to figure out, what do we want this air taxi to look like? And then I had basically mass targets and a bunch of other random requirements for crash, interface loads, passenger, pilot, you name it, luggage, whatever. And where do we put frames? Where do we put crush structure? How do we make sure that it behaves the right way? Do we want to weird things like a parachute or no? Kind of a lot of different trade studies in that space. So I was doing a lot of optimization there, actually. So this was a lot of really basic optimization, but I was doing a lot. So just some basic sizing optimization and OptiStruct, and then just a little bit of detailed analysis, but actually not too much. It was kind of a fun system level thing. Then in June, I took over as this is also a fairly random, or maybe call this one a right turn. Took over as battery module engineer, and then also took over as a lead for the electrical distribution system on one of our prototypes. We basically had an issue with our prototype. We needed to redesign it, and then I took that over. So it's kind of been doing that since June. Basically trying to design new batteries and energy distribution systems that we can actually fly in the very
I have a
near term.
question, Dan. That's very interesting. So when one decides to switch not careers but almost like a different area to a different area of expertise, what do you do to overcome the fears that everything may be okay, you and a lot of people don't want to do anything different because they're worried about that the lack of confidence. What give you the confidence to do what you're doing now?
Yeah, just ask lots of questions, and this is a bit of goes back to what I was saying earlier. Is you're always, well, fortunately in this instance, I was surrounded by a lot of people who had lots of expertise in this area. However, they were missing someone who saw the big picture. So what I was actually originally brought in to do was just design the structure for the battery. And I did that. I mean, you can see as going through my job experience, I have a lot of experience doing that. And then they were like, oh, we actually need the rest of the electrical system to be figured out. And I just started asking lots of questions, trying to understand and trying to leverage the experts who had their own individual skill sets. So, we had a guy who was an expert in high voltage safety. And I would basically ask him endlessly questions about, whether or not we're meeting certain requirements. Do we have the right requirements? Do we have X, Y, Z? And then over time, you begin to just develop an intuition about these things, even if you're not an expert. And the most important thing is you're always part of a team. So you have to remember that you can't do everything yourself. But if you use the team, usually you can become more comfortable with where you stand on these kinds of career changes, if I call it that way.
How do you gain the respect of others? So they know you're a structures person leading a battery team. So how do you gain their respect in terms of being a lead for an area that maybe not be yours right now, but you are leading them very well, obviously. So how do you get that camaraderie to work your way?
Yeah. Well, two things. A few things actually. So the first and most important thing is they just needed someone to help. They were just lacking a person to be able to do it. And I felt comfortable stepping up and assembling a team basically to help me. The next thing is, I don't know how to say this any other way, but just to deliver and deliver a product that works. So what we did is fairly early on when we didn't have anything, I basically asked us to try and make something that's minimum viable product that works so we could prove to people that we can build the production one. And we did that. And that, I think, gained the respect of everybody on the battery module team to be able to do that, despite the fact that I was just a structures guy. So, And then also again making sure that the whole team is leveraged, and that you're not just the structures guy making a battery. You're the guy who can design a battery and also happens to know a lot about structures. To think about it that way.
Yeah, so basically step up to opportunities that may show up if they're available, and then kind of lead the team if that
Yeah.
comes up, right?
Yep. Yep.
That's very, very cool because a lot of engineers, we tend to fear making that move in fear of getting embarrassed because maybe I don't know much about electrical connections and things like
Right.
that.
Right.
But your approach has been, let me learn from people around me, right? And
Yep.
that's,
Exactly.
it
Yep.
comes across humble as well. So
Yeah, I think it's always good to think that way, because everybody has different experience, and you're generally better off if you leverage everybody else's experience too. Yep.
very nice. And there's a question here in the chat that talks about parachutes and the packing science, and this being a difficult problem to model. Do you have any insights into the testing analysis or anything along those lines?
Yeah, that's actually something I don't have any experience with in terms of modeling, but was a huge focus area for us for what we're doing at Lillian. I can't talk too much about exactly what we were doing, but all I can say is I didn't have too much involvement in the analysis of the parachute side of it. Um, at, completely unrelated, but related to working with a team. One of the things we were working on at SpaceX was parachute unfurling analysis for the Dragon capsule. A lot. And I think we developed a lot of really interesting methods there. But a lot of that was explicit, like I think we were using Abacus Explicit to do some of that modeling. It was quite complicated though.
Yeah, a lot of the dynamics with explosives or parachute deployment, things like that, those are typical softwares would be like LS Dyna, Abacus
Mm-hmm.
Explicit, stuff like that, right?
Mm.
Is that what you're talking about?
It was LS Dyna. Sorry. Yep. Exactly.
And to connect it to the course that we're teaching here, when we talk about explicit methods or implicit methods, we're talking about time marching the solution forward. And if you were to try to analyze these very, very challenging events with implicit models, it will take forever to run. And that's why explicit models are used, because you basically time march the solution using the forward difference method. So just to connect the dots for you guys so you can see the connection there. So very, very neat. And that's a picture of you where
Yeah, some personal stuff. I figured I'd send a fun picture of myself rather than a boring one of me in a suit or something. This more describes me. This is this is on the border of Austria and Germany, near Zugspitze, but actually in Mittenwald. So it's on one of the peaks over in the border. I'm in Munich. That's only about an hour south of me. It's pretty cool.
very cool.
Yeah.
So while we don't dive into very impressive. Thank you so much for going through. One of the things I like about inviting people successful in industry um, is that we get to see the career path, and you can see here clearly that I don't think Dan knew that in 20, I don't think you knew that in 2012 you'll be in Germany in 2020, right? Am I
Right.
wrong?
No, you're right.
And I don't think you ever had in your head that you'll be some sort of battery module lead.
Right.
And so one of the things I want to pass along to you guys, because I hear this question a lot during discussions, one-on-one discussions, is, where do I go from here? I'm going to graduate. What is my next step? And I think what we're hearing is sometimes you just try to do something that's interesting, that's exciting, and you try to use the opportunity to learn as much as you can, and let
Yeah.
let life be an adventure. You can try to plan life all day long, but it may not turn out the way you think it's going to be. And so it's important to kind of follow your heart, kind of keep learning, right? Am I wrong, Dan, about this? Or
No, no, you're totally right. I mean, yeah, basically every move I made was just trying to do that. And then, if new opportunities present themselves, like be very open-minded is also very
and
important.
you didn't predict that COVID was going to hit while you were in Germany. So Um,
Unfortunately, no.
right. But you're pretty sure that will make you stronger. It will make us stronger. Everybody will
Yeah.
become stronger after this. I hope that's the case. But then, in all these experiences that we see here, I assume that finite elements did play a role in making those projects successful.
Yeah.
And so
Big time.
we invited you to kind of give that perspective, if you want to dive into this one here.
Yeah. Cool. So I went for a less technical but more I don't know, kind of almost philosophical aspect because I didn't talk, I mentioned FEA in a lot of my experience, but I think Vinay is going to give you guys the best technical background you can get. But the thing maybe I can help with is not like lessons learned, but like important ways to think about, how we use FEA, why we use it, when not to use it, and when to be careful. So there's kind of four key topics I see here to share. This is not comprehensive. These were the four that I thought were most important to chat about. So one, not everything's testable. Two, in aerospace, margins are low, mass is critical, and you never have infinite time. Three, all models are wrong, but they have to be useful. And then the last one is a fairly quick but very important topic on the building block approach for analysis and how that can save money and a lot of other things, actually. Yeah.
A little bit of a question here. We talked about margins are low, mass is critical.
Yeah.
And that's a very interesting point because civil engineering structures, you can make them very, very heavy.
Yeah.
And when I first start working on rockets, not even airplanes, I think airplanes have a good factor of safety. But when you
Mm-hmm.
look at rockets, that could be slim margins and slim factors of safety. Sometimes I wonder, you can be too off, right? And what's your perspective on that?
Yeah. Well, I mean, that's actually, I see FEA was crucial to everything we did at SpaceX because you have the same margins, I mean structural margins, right? Extremely low structural margins in general, and very low safety factors. Um, and also, I think the environments were always hard to predict too. So you have this like really, really, really tight design space, um, and and what are you going to do other than try and understand the problem as well as you can, and like you can test, but testing doesn't get you everything. It's kind of what I'm going to talk about in the first point.
And
um,
and margins are low in general, not just at one company. They're low, like generally
right.
speaking.
Right.
That's basically the way it needs to be, right? Otherwise, how are you going to deliver a payload
Exactly.
efficiently, right?
Yeah, like every ounce counts, for sure. And yeah, in space it's really hard. In aircraft it's hard as well, but do have big safety factors and usually redundancy. I mean, yeah, it depends on what type of aircraft, but you have a lot of other things that are going to save you at the end of the day, and especially in rockets and spacecraft. Well, yeah, I'll speak more to rockets and spacecraft, but there's not much there to save you. Not much redundancy, and you don't have much material to add usually. Yeah.
Yeah, I can't wait until we discuss number three coming up, because that's very provoking, thought provoking. All models are wrong, but they're useful. So
Yeah.
very curious to see where you're going with that one. There is a question about when we say margins are low, what does that mean?
Yeah, I'm talking about yeah. Well, what am I talking about? I'm talking about everything actually. So I mean structural margins in the context of FEA, but it actually means performance margin, right? So like I don't if I'm designing a stage for the rocket, I don't have much mass margin. I have probably none if I do a layout and then do my initial sizing. I probably don't have enough mass to begin with. So I'm already probably either negative or whatever. And then because of that, my structural margins are low. And then you may also have other margins for thermal or yeah, trajectory related items as well. So you're really just in a very tight design space. You're in a tight design space, basically.
Very cool. So I'll go here. Let's try to hit the first point there.
Sure. Then tell me to speed up if I'm going too slow, by the way.
No, it's pretty late over there, so I'll leave you to decide what the pace should be. But so far, I think
Thank
it's
you.
very, very good and very valuable, in my opinion.
Cool. Cool. Okay. Just trying to move my, there we go. All right. So I think like the useful, so not everything's testable. So the useful thought experiment for me, like when I'm trying to explain this topic is if testing was incredibly cheap and also really fast, would we even bother with doing structural analysis? Like specifically, just talk about FEA. So I don't know, the way to think about that is, okay, what could I do then with testing? Well, if I have a really complicated structure, structure meaning structure of X, of a mechanism, of a secondary structure, of a primary structure, or whatever. In aerospace, usually you have a lot of different design environments, a lot of different conditions that you're going to see on your part, meaning different manufacturing variability. If you have a welded part or a composite part, you're going to have different defects in different areas. The material itself will have variability, and you'll have to figure out how to combine all of that. So even if we can do essentially infinite testing, it's really hard slash almost impossible to cover all of those conditions with testing. So it becomes quickly impractical, even if we just do it in a theoretical way. So the thing to remember is physics will always win. I think this is, for me, I like thinking about this way. Like you can't beat physics. It's always going to win, right? So if we consider all the different combinations that we have to have, meaning test like you fly, you have the right temperatures, the right structural loads, which could be a ton of different combinations, and dynamic loads, and the part side of it, so material variability, manufacturing, your part's going to fail if it's not designed to meet those requirements. Or it has a high likelihood of failing. I think when I say failing, we have to remember that usually just means a high likelihood of failing. So this is kind of where FEA really becomes helpful, is because you can assess each one of these. You can assess a reasonable number of these different conditions in order to de-risk whatever you're working on. I use the word de-risk here because you can never be 100% certain on anything. However, following good analysis guidelines, and being well trained in your tools, peer review, and kind of understanding where your strengths and weaknesses are, you can get a really far way to understanding whether or not your part's going to work. Or even, almost more importantly, you can get to a point where you know what you want to test. So you can say, I looked at 1,000 different conditions, 10,000 different conditions, including material variability and manufacturing. And this is how I need to test in order to be sure that it's going to work. So in the real world, this is actually how it's normally done. Usually you use FEA to write your structural margins and do X, Y, Z. And then testing is somewhere in that timeline included. And FEA, when done, I think when programs are generally going well, we see that FEA is used to down select load cases, figure out where we predict we're going to fail, and then going and verifying that, and then tying your model back to that at the end of the day. Any questions about this topic?
Yeah, I do have a question. So Not everything is testable, right? So like that's true. How you build the confidence that when you're analyzing something that is not testable, that you're in the right track, because it's almost like you're doing this in a void sometimes. It's in a vacuum. Is a better word. Any thoughts on that?
Yeah. I mean, yeah, the most useful thing to do that I try and do when I'm kind of starting out on analyzing something or even reviewing something is considering the failure modes that you expect, or even simply listing them out and saying, okay, here's the failure modes I would expect in this part. It has a bunch of bolts, it has some welds, it has composite parts, whatever. And then kind of figuring out how am I going to go assess each one of these. So developing basically a structural analysis roadmap. Um, and then if you have this roadmap, you know the failure modes you want. You can kind of figure out how to get from your inputs to those outputs. Outputs meaning failure modes and margins on those failure modes. And then what models do I need in between? What analyses do I need? And you start to develop an intuition without even having the model results yet. I'm just thinking about it. You know, where are my sensitivities? So am I very sensitive to temperature, or no for my worst case failure mode? Likewise for material variability and manufacturing, that kind of thing.
And perhaps there's a way to validate your FEA model against cases you can test, and perhaps use that as a transfer function to believe that your FEA model is good for cases you cannot test, right? Right.
Exactly. Yeah. So it's always best to this one goes back to the building block a bit at the end. For me, it's always really important to use methods that um, uh, get the job done, but aren't too much. But at the same time, you know how to check in simple ways, or that you already know are grounded in reality, meaning they've been anchored against some test which is similar to the thing you're looking at, or you plan to do that, or you have done it and you're checking it already. Cool.
So what about this idea of margins are low? We were talking about this earlier.
Yeah, perfect. So um, yeah, in reality, like actually testing, I'm not going to say testing is expensive and time consuming, because I actually don't think it has to be. But I think it definitely can be. And you have to find a balance. So, you know, if we had huge mass margins, we probably would just overcompensate with adding more material to de-risk failure. And like I think actually mentioned, I think Vinay, you mentioned it, civil engineering earlier. Like usually things have high safety factors and are more like designed by handbook, which are heavier than they need to be, but kind of get the job done with minimum effort. Even civil engineering uses FEA though, so we can already see that that's the case where it's still useful. Um, yeah, and then my next point is even if you have these high mass margins, you usually have lots of time pressure. So I might be able to do a test, but I might not be able to do my test either too late, or I don't have, who knows, I don't have enough support to do it. Yeah, your FEA becomes kind of an invaluable tool here. Yeah, it's really just the most economical way to ensure that the flight hardware is going to meet its requirements. I do see a couple exceptions here, like a couple that come to mind in the near term projects I've worked on. So it can be hard to leverage only, well, not only FEA, but really leverage FEA heavily if it's an extremely complex analysis that you don't have either confidence in doing yourself, or you don't have good experience with it. In particular, when it comes to things that are hard to ground to reality. So, like parachutes was actually one of these things that I recall. It was so hard because it was like high up on the building block pyramid, like a lot of different inputs, a fairly complicated analysis. It was very hard to test and very hard to ground models. So we were trying to figure out, how do you ground a model to a test, because you have like video and load sensors, and it was really, really hard. But at the end of the day, even that was very useful. We just had to really struggle through it. So it's a bit of a balance. And then another one that I see is a bit of an exception is where you have really uncertain inputs. So garbage in, garbage out situation. I've been working on batteries for pretty heavily for almost a year now. And we really struggle there because we're using materials in really, really high temperature environments that are basically seeing really high temperatures for really short periods of time. And we don't have great material properties. So we're doing structural analysis basically to steer ourselves in a direction, but we don't have a super high confidence in the results at the end of the day. But these are, I guess, they're exceptions, but they're more things to be aware of, I guess. Okay. Is there a part 2 to this one? Yes, there is. Okay, so in summary, yeah, FEA should always be a tool in your toolbox. I think even when I say a tool in your toolbox, you're probably gonna get your master's degree and then you're gonna use some FEA in your day-to-day, but maybe you're not gonna use it in your day-to-day 10 years from now. So I think it's important to think about, if you know how to do this work and you know what it's meant to be used for, you can still use it as a tool, even if you're not using it, if you know what I mean. So obviously, as a design engineer, this speeds up design iterations you can do. So you can basically do these virtual tests nearly, I mean, not for free because time is money, but for free. So you don't have to set up a test and do everything. You can just look at your own design and try and find the most optimal design. And then obviously as a stress engineer, this is the main thing you're doing. But then kind of like bigger picture, as a program or product lead, realize that FEA is quantifying risk for the program, and you can use that as a tool. Even if you don't know if it's giving you, if you don't have all the right inputs, you can still use it to say, okay, this is directionally correct, or that is. And then, yeah, as a systems engineer, it's crucial for compliance deliverables. So you don't get a certified vehicle without having FEA, basically. It's very hard to do that. Okay. And then, yeah, also consider that FEA is not only a stress tool and not only used to write kind of strength, buckling, or yield failure margins, which you might just see in stress reports, but it's used for a lot of other stuff. Just listed a few here. There's like thousands more, but optimization for aircraft layout. I've used OptiStruct to do this. There's lots of programs that do this, but OptiStruct's pretty good. Vehicle level dynamics models, like coupled loads analyses. We use this at SpaceX constantly, basically using that to create loads for your stress models. And then one of my favorite things, kind of going back to the design topic, is exploratory analysis. So kind of, what if we did this? What if we did that? How can we basically be creative with the design process and use FEA as a tool in there? Yeah, I think that's everything for this margins is low, mass is critical, and there's not infinite time topic. Great. Okay, so it's a bit of a cliche saying, but I think very relevant for FEA, especially. I've had a lot of experience personally with this one. Basically, you always have to be sure. So remember, all models are wrong, but some are useful. I think all models are wrong is like a bit too strict here in engineering. If all models were just wrong, we wouldn't use them. We would find something better. Really, it's just there to be risk reduction or provide some measurable performance benefit. I think there's really two things that jump out to me. I'm sure there's more. Two things that jump out to me as being actually detrimental versus helpful in the design and certification process with FEA. If we kind of fall into these traps. So one, if your FEA is not grounded in reality, meaning you're using methods that are too complicated for the problem you're trying to solve and are challenging to correlate back to some test, well, that's more of an or statement. Methods that are too complicated or that are challenging to correlate and test are generally not good. So if I have a bracket holding something onto the side of a rocket, and I'm using LS-DYNA fully explicit analysis with nonlinear everything, I don't know if I'm going to be able to get a useful model out of that. I think you probably can, but usually that's completely unnecessary, and it's harder to understand. Can you do that with a hand calc? Maybe. Kind of depends. Don't want to say all brackets are super simple because they're not. But you can use a pretty simple FEA model to do that. And you can use a pretty simple FEA model that you can also check by hand and using solvers that, let's say, 90% of stress engineers know how to use. So you can easily have it checked. You can easily go check it yourself. You can go poke around and try and understand it. You don't always have that luxury. Sometimes you're working on something that, like a parachute, where, you know, Nastran Solution 101 will not do it for you. However, maybe go for the simplest tool that you know works. And always ground your FEA in either, well, definitely in a test somehow, some way. Meaning you basically instrument your test, and then you use your model to take a look at whatever instrumentation you had on your test and correlate it back to that model, and make sure that it matches. And if it's not matching, then you have to go and fix it. And then you have to go and reassess your structural margins. And then either you have to retest or you have to show that you still meet all your requirements. And then, of course, using hand calculations to ground your FEA model is good too. But your hand calculations also maybe should be grounded to a test in any case. So,
I
yeah.
also wanted to point out that some tests are also wrong because you may define a test program using finite elements and the finite element was wrong in the first place.
Yeah.
Can that happen?
Mm-hmm. Yeah, absolutely. So, I mean, yeah, this is getting a bit again. Yeah, like, how do you ensure you've designed the right tests? This is where I think that actually, like, the systems engineering side of it becomes quite important. But yeah, that's of course possible. Yeah. Good. Okay. Yeah, 3 things that I recommend following for FEA models. Always be distrustful of your results and kind of work backwards to gain trust in them. So especially if answers are like looking really good, everything looks great, definitely question what you're doing. So I put a link in here for the anchoring effect because it's like classic one that I always fall into. It's like, oh yeah, everything looks great. Okay, let's send it out for peer review, and like you miss, okay, you use the wrong material properties from the get-go. So I was, getting that stuff checked. So peer review, supporting hand calcs, sensitivity analysis helps. Always use a checklist. And if your company doesn't have a checklist, make one for yourself and use it, so that you force yourself really to think about all these things, because just quickly run through them in your mind. It's very easy to forget them. And sometimes these very, very easy things are the easiest ones to miss if it's just you working on it. At least it's me personally. I think I work that way. And then follow the building block pyramid approach for structural analysis, which we'll talk about at the end. Yeah, I think I already belabored the last point. Perfect. Okay. So building block approach for structural analysis. is a pretty helpful diagram here. I don't know if anybody's familiar with the building block test approach, but it's fairly simple in that you basically start at the bottom with things you have extremely high confidence in, which basically are very low cost. MMPDS is a bit outdated, Mill Handbook 5, but yeah, using standard fatigue fracture information, and then working your way up to things like a simple FEM that can be checked, then an intermediate FEM, a complex FEM, and then advanced methods. So if you're finding yourself at the top of this pyramid from the get-go, you probably either are right at the cutting edge and tried everything else from the bottom up, or you're probably starting in the wrong place. So it's always good to reconsider, am I starting at the most appropriate tool that I have the most confidence in before setting out and doing all the work. I've seen a lot where we start with the most complicated method, spend lots of time on it, and then a bit failed to take a look at the bottom of the pyramid, and then we miss something. We got to start over, or we just scrap it and make a simpler model. Yeah. Okay.
So basically, start here, validate your models, and then increase the complexity, so that when you get to the point where you can apply it to the full scale system, you don't have a failure late in the game that could cost a lot of money, right?
Yeah, exactly. And sometimes it's easy to plan these things so you can say, I have PDR in a month and then CDR in 3 months, and I can have my simple FEM validated and a bit ready to go for PDR, and then between PDR and CDR, I can do my intermediate complex FEM, and I have my advanced model ready to go before flight to check for everything else, for example.
Okay, thank you so much, Dan. Any questions? I think this was a great, great preview or great introduction to some philosophical points about finite elements. And just to recap, we have them here too. Let's just go back here in case you have any questions. So with that said, any questions?
Hey, Dan. Don't know if you remember me, but we almost worked together at SpaceX for a minute. Right before you left, you were going to do like a buddy review for me or something like that. And then suddenly I got the no reply email.
Okay.
Anyways, yeah, I'm good buddies with Clayton Button. I think you know him over there.
I work with him here. Yeah.
So
that's great. Yeah.
Say hi to him for me.
Sounds good. Will do.
Any other questions? The world is small. The rocket world is small.
Yeah, it's really small. It's actually, the whole world is really small, even outside of rockets. Like, yeah. I'm working with, there's a question here, what inspired me to move to Germany? This is a perfect example. I worked with someone on Echo Voyager, the submarine. This was like the first thing I worked on in my career, who I kept in touch with loosely. And he's actually the one who got me this job in Germany. He basically just reached out and said, hey, do you want to do structures work in Germany? I was like, sure, why not? So it was just kind of like a fun thing for me. So I took it on, but always keep your connections handy.
And that's a good point. Keeping those connections is of great importance, not only because you can have mentorship outside of your area, but also maybe new opportunities arise. And, I do value that. I think that's a great point.
Yeah.
Any other questions? That was a great question there. That turned into lesson learned. How do you market yourself if the projects you work on are more things that you cannot share widely. So, for example, say you're working on something, but you're not allowed to disclose it to anyone, no future employer. How can you market yourself if you were in that situation?
Yeah, that's a good question. So, I have an answer. I hope it's a good answer. So basically, I'm a strong believer in. Now I'm going to talk about hiring. I'm a strong believer in hiring for skills versus experience. And so, for example, at SpaceX, we had a guy who joined our team, and he worked in oil and gas his whole career. And then he started working on rockets, and he was freaking brilliant. And he didn't know anything about rockets. He didn't know anything about aerospace in general, but he was a great structures engineer. And it didn't even matter what I didn't know what he worked on, ships and oil platforms. I had no idea what exactly he did. But he had the skills to do the job. And at the end of the day, when you're interviewing, well, I'm of the opinion personally, I think maybe this isn't shared by everybody, but it shouldn't really matter what exactly you work on. It shouldn't matter exactly, did you work on this project or that project or whatever. If you can show up and you have the best skills, if you're the best engineer, regardless of what you've worked on, you're probably super marketable. So I always think it's good to try and play your skills up and on your resume and in the interview, then talk about specifically the maybe projects you can't talk about.
You can always generalize very top level the impact you had.
Yeah. You can even, I mean, usually like what's useful is interviewers will ask you questions and then you start actually answering their questions with those skill sets somehow. You can usually demonstrate that in an interview, what have you.
How you market yourself if you want to apply to a position that you really want, but you have no expertise on. What is the best way to sell yourself for that situation? Not sell yourself, but how to market yourself.
It's a good question.
I think it goes back to your point. You can sell your skills. You can tell them what skills you do have. And I assume that one of the responses will be that you're a willing learner, right?
Yeah, that's always a part of, actually. I mean, that's a big part of it is you have to be open-minded and willing to take on new responsibilities. So yeah, that's an area where, demonstrating willingness to work on new things would help you. So that's one experience point that would help you. Maybe not a specific experience, but if you can show that you've worked on a lot of different things, you're likely to get a new thing working on something that you think is interesting, but you haven't worked on in the future as well. Yeah.
Very, very, very nice. Thank you, Dan, from Germany. You're located at. I appreciate you making the time at 2 in the morning to talk to us and teaching us about the philosophical points of finite element analysis and talking to us about career, like how the career can actually be. When I look at this right here, it's not clear if you knew at any given point where you're going. And a lot of us, including me, struggle. What we struggle with making those hard choices of moving to a new area or where I'm going to do next, and so forth. There's also the idea that life is an adventure, and I think this picture above here kind of demonstrates that you're like probably backpacking or hiking. But life is an adventure. We don't know where we're going at any given point. So we should make the most out of it and have a good time, right? You're having a good time. Would you say you had a good time so far in your career?
I've had a lot of fun.
A lot of fun. Okay.
Yeah.
And when you say a lot of fun, I assume that it's exciting, right? Exciting to work on all these different things.
Yeah, of course. Yeah. This thing in Germany has been very interesting for me too. Obviously, working with people in another country is good. So I've gotten a bit to see, what's it like working with, SpaceX was full of genius, crazy people, and I'm working with a bit of a different group. German engineering is very slow, methodical, super detail oriented, super detail oriented, and yeah, just a bit more following the processes, doing it right, so on and so forth. That's been fun too for me.
Very, very cool. Well, thank you, Dan. I think we should let you rest. I appreciate it. I think all of us here I learned a lot from you, so I appreciate that.
Yeah. No worries. I have my LinkedIn at the bottom there if anybody wants to reach out. I don't know if you get that. But yeah.
And a lot of
Thanks for
folks are saying
inviting me.
thank you. Thank you for staying late to give us this talk. A lot more thank yous dropping in. We have about 60 thank yous, I think, coming in. So
cool. Thank you. All right,
well,
guys.
thank you. And by the way, we do have students all over the world because of COVID that could not all travel to California. So I'm pretty sure there's folks at different time zones all over the world. So I appreciate you guys also calling in. Okay, with that said, thank you guys, everybody. And thank you, Leonardo, for the awesome guidance as well. So I appreciate that earlier in time when you did that. Dan, it was great to see you. We need to do this again. Appreciate it.
Yeah, anytime. Thanks.
All right.
Thanks so much.